That ancient dream, right?
Yeah.
Turning dull, heavy lead into, well, gleaming gold.
Yeah, it's the stuff of legend, isn't it? Drove alchemists for centuries.
Absolutely. But get this. Scientists at CERN, the Large Hadron Collider,
The LHC, yeah.
they've actually seen it happen. They've observed gold being formed from lead.
It's pretty amazing. There's a new study out just published in physical review journals.
From the Alice experiment, specifically.
That's the one. It details how they saw this.
Okay, but hold on. Before everyone starts, ripping out pipes thinking they'll strike it rich.
Right? Let's manage expectations here.
This isn't, magic or old school alchemy, no philosopher's stone involved.
Definitely not. This is modern nuclear physics, pure and simple. Or, well, maybe not simple, but physics.
Right. So our mission today, for you listening, is to unpack how this works. How do they actually do it? Why is it important scientifically? And, does it mean anything for the gold-making dream?
Exactly. We'll get into it, keeping the super technical stuff, manageable.
Okay. So the old alchemists, they had this idea, chrysopoeia.
Right. The art of gold making. They saw lead and gold were both really dense.
And figured maybe one could turn into the other.
Yeah.
Based on just that similarity.
Kind of. It made a certain sense back then, given what they knew, or rather what they didn't know about elements.
But we know better now. Elements are defined by protons, and chemical reactions just don't change that number.
Correct. Basic chemistry won't turn lead into gold. That's off the table.
But nuclear physics, that changed things, didn't it?
It did. Early 20th century, we figured out you can change elements by messing with the nucleus.
Through things like radioactive decay. Or in labs.
Both. Radioactive decay happens naturally. And yeah, scientists have made tiny amounts of gold in labs before using particle accelerators, hitting targets. It's called nuclear transmutation.
Okay, so making gold in a lab isn't totally brand new. But the Alice experiment, they found a new way this can happen.
That's the really interesting part, yes. It involves these lead atoms whizzing past each other incredibly fast.
Like really close encounters, but not actual collisions. Near misses.
Exactly. Near misses at almost the speed of light.
How fast are we talking?
The number is staggering. 99.9999993% of the speed of light.
Wow. Okay. So in the LHC, they slam beams of lead nuclei together, usually for those big, messy collisions.
Right. That's what it's famous for, creating showers of particles. But sometimes they just skim past each other. Really, really close.
You mentioned an analogy, like two super fast trains.
Yeah, imagine them roaring past on parallel tracks. They don't hit, but the forces between them, maybe the air pressure, would be huge, right?
Okay, I can picture that. So here it's not air pressure, but electromagnetic forces.
Precisely. Lead has 82 protons in its nucleus. That's a lot of positive
That
charge.
creates a strong field.
A very strong electromagnetic field. And because they're moving so incredibly fast, relativistic effects come into play. The field gets kind of squashed.
Aquashed. How so?
It becomes flattened in the direction of motion, forming this thin, intense pancake of essentially photons perpendicular to the direction they're traveling.
A pancake of photons. Okay. So this photon pancake from one lead nucleus interacts with the other lead nucleus as they pass.
Exactly. It's not a physical crash, but these high-energy photons basically slap into the other nucleus.
And that interaction, that slap, can do something.
It can. It can excite the nucleus, transfer energy to it, and this can cause what we call electromagnetic dissociation.
Dissociation, meaning it breaks apart slightly.
Yeah, it can make the nucleus eject some particles, neutrons, and crucially for this story, protons.
Okay, protons. Right. Let's connect the dots. Gold is element 79, so 79 protons.
Yep.
Lead is element 82. 82 protons.
Correct.
So to get from lead to gold, you need to knock out exactly 3 protons.
That's the magic number here.
Yeah.
3 protons need to be ejected by this photon interaction.
And the Alice detector, it can actually see this happen. It can tell if 3 protons got knocked out.
It's incredibly sophisticated, yes. It can distinguish these events from, say, 1 proton being ejected, which would make thallium, or 2 making mercury, or none, where it stays lead.
Wow. Marco Van Leeuwen, the spokesperson, mentioned how sensitive it is, right? It has to handle the chaos of head-on collisions and these much quieter near-miss events.
Exactly. It's designed for both extremes, which is quite an engineering feat. It can count those ejected particles.
So how do they actually count them? Is there a specific part of the detector?
Yes. They use what are called the zero-degree calorimeters, the ZDCs.
0 degree, meaning right along the beam pipe.
Pretty much. They catch particles that are scattered only very slightly from the original beam direction, which is typical for these near-miss interactions. Analyzing what hits the ZDCs tells them how many protons were lost.
Okay. So they ran the numbers. How often was this actually happening? How much gold were they making?
Well, the peak rate they measured was around 89,000 gold nuclei being formed per second at the collision point inside Alice.
89,000 a second. I mean, that sounds like quite a bit, doesn't it?
It does sound like a large number initially, but, and this is a huge but,
Here comes the catch. I knew there'd be one.
there always is, isn't there? These gold nuclei are created with enormous energy. They're still traveling incredibly fast.
Yeah.
And almost instantly, they smash into the beam pipe walls or the collimators, those devices that clean up the beam.
So they break apart immediately.
Poof, gone. They fragment back into protons, neutrons, other stuff. The gold exists for maybe a trillionth of a second, if that.
Fleeting gold indeed. So created and destroyed almost simultaneously. Okay, what about like over a long run? Did they estimate a total amount?
They did. They looked at data from LHC Run 2, that was 2015 to 2018.
Okay.
Over that whole period, across all the main LHC experiments, not just Alice, they estimate about 86 billion gold nuclei were produced in total.
86 billion. That still sounds like a lot of nuclei. Is that enough to, I don't know, see? Make a tiny flake?
Not even close. 86 billion gold nuclei works out to about 29 picograms.
Picograms. How small is that?
That's 2.9 times 10 to the minus 11 grams. It's indescribably small. Trillions and trillions of times less than you'd need for even the tiniest visible speck, let alone jewelry.
Right. Okay. So the alchemist's dream of riches. Still very much a dream.
Very much. Even with Run 3 producing maybe double that amount, because the LHC is running brighter, more collisions, we are nowhere near making usable gold this way.
So technically, yes, lead turned into gold. Practically. Not so much. The headline is maybe a bit more exciting than the reality for treasure hunters.
Precisely, but that doesn't mean it's not significant scientifically.
Right. Uliana Dmitrieva from Alice pointed out this is the first time they've systematically detected and analyzed gold production like this at the LHC.
Yes, it's a first. And the value isn't in the gold itself.
So what is the value then, if not making tiny, fleeting bits of gold?
It's about understanding the process, testing our models of how these electromagnetic interactions work at extreme energies.
Understanding the electromagnetic dissociation better.
Exactly, and that has practical uses. John Jowett, also from Alice, mentioned this. Understanding these near-miss interactions helps predict and manage beam losses in the LHC.
Beam losses, like particles straying from the beam.
Yeah, particles hitting the pipework. It's a major limitation on how intensely you can run the collider if you can predict these electromagnetic effects better.
You can maybe operate the LHC more efficiently?
Yeah.
Or design future colliders better.
That's the idea. It feeds back into making these incredible machines work better and pushing the boundaries of what we can explore.
So it's not about the bling, it's about the physics. Understanding fundamental forces and improving the tools we use to study them.
That's the real treasure here. Knowledge. A deeper insight into how nuclei behave under these extreme conditions.
Okay, so let's just quickly recap for everyone listening. That ancient quest led into gold. Scientists at the LHC have actually seen it happen.
Yep, high-speed lead nuclei doing near misses, generating intense photon pulses.
Which knock out exactly 3 protons from another lead nucleus, turning it fleetingly into gold.
Fleetingly is the key word. The amount is unbelievably tiny, gone in an instant. So no rewriting the economics books.
Right. But the real payoff is understanding this process better, testing physics theories, and even helping to improve how particle colliders like the LHC operate.
That's the takeaway. A fantastic piece of physics, even if it doesn't fulfill the alchemists' original materialistic ambitions.
It really makes you think, though. Science chasing these fundamental questions, even something that sounds like ancient alchemy, it can lead to unexpected knowledge, unexpected benefits for the technology we rely on.
Absolutely. What other seemingly impossible things might we unlock down the road? And what surprising applications might they have?
Definitely something to chew on. Different kind of gold, perhaps.